Hi, in this session, we will fix the bouncing problem of a physical switch in a FPGA board. So, if you remember from our previous session, we designed our LED pattern system. It was shifting the LED when you press your button on the FPGA board. But we faced some problem that when we single press our switch, it was shifting more than one LED, right? But we were expecting that when we press the switch, then our LED should shift to the right by one precision. But unfortunately, it was shifting by more than one precision when we were pressing our switch, right? And we found that it was happening due to the bouncing problem of a physical switch. Then in the last session, we explained that what is that bouncing problem in a physical switch, why it happens, and how we can solve this problem. So a quick brief that in bouncing problem, you press your switch once, but it gets captured as a multiple activation. So your LEDs were shifting multiple times. So in the last session, we discussed that. And we discussed the strategy to solve this bouncing problem with the help of VHDL code and logic, right? So if you are still not clear about the bouncing problem of a switch, and if you do not know the logic that how we are going to solve this problem, then please watch my last video to understand the logic which we are going to implement in this session. Okay, so enough introduction. Now let's move to the Quartus Prime software and implement that debouncing logic into our LED pattern project. Okay, so now it's the time to design the same system like LED shift registers with debouncing feature of that switch. Okay, so we have explained this problem, right? That what will happen if your switch bounce because that is a mechanical system or that is a physical hardware, right? So you might try to press it once, but that is having the mechanical in nature. It can give multiple pulses, and because of that, your shift registers jumping to the multiple LEDs means instead jumping of one flip flop, it jumps multiple flip flops. Okay, so that was the problem. Now we will solve that problem with the debouncing of switch. Okay, so this is the same code from our last session, and we are just updating that. Okay, so a quick brief. This is our library declaration. This is our entity section. So we have this project 01. We have clock as an input, reset as an input signal, and switch as an input signal. We have one single output, but that is having the four elements. So we have four LEDs as an output. Now this is the architecture section. So we have defined few signals. We explained what are these signals and what they do in this program. So I'm not repeating that again, but we have this shift process. This is doing the shifting operation. So when reset is asserted, we have this shift register as in default value 1000. We explained why it is having this value. And if button is pressed, then your shifting operation will be taken only at the rising edge of clock because this is a registered process block. Okay, so this is sorted. So this is doing the shift operation when this button pressed is equals to 1. Okay, now we have defined this process sync. So what it is doing, we are having this switch that is asynchronous in nature. So we have synchronized this input. Okay, so for that we have this sync process. Okay, and in the last we have this switch detection process. Okay, so it is detecting that if button is pressed or not. Okay, so if this condition is met, means when your signal is going from logical high to logical low, then we are saying that button is pressed, and when it is not happening, then we are saying button pressed is 0. And we have reset condition as well. So we are saying delay switch is 1 and button pressed is 0, means it is not pressed. Okay, now what we need to do that we need to improve our synchronized version of our switch. Okay, so we are not touching this switch input because that is asynchronous in nature, and we have already synchronized it with sync 1, right? And we are using this here, right? So as I explained in my last session, we are needing few additional signals for that. And these are one for the counter. So define that signal, give some name. So suppose this is counter and this is integer, and give some range. So I'm giving range 0 to. Now we are needing one threshold as well, right? So define a constant, and that is our debounce period, suppose, and that is integer type, and it is having the value of say 25 million. Okay, so we have defined this, and now we are needing one additional signal. Okay, because till now we are using that sync one as in switch detection, right? So we are needing one additional input. So we are saying that is signal, give some name. Suppose this is debounce switch, because we have down debounced it. You can give any name, right? So this is again std underscore logic type. Okay, now we need to write a additional process to debounce that input switch. Okay, so give it some name. So I'm giving process for debounce. This is again a registered process block. So reset clock is in the sensitivity list. Now begin. So create the structure first. If reset is equals to 0, then do something. Else if at rising edge of clock, then do something, and in the last and if, right? So first write the reset condition first. So what will happen at reset when reset is applied? So our counter should be 0. So that is the first thing that we need to do. And what else? We will debounce our switch as well, right? So we will reset it to some value. So give it debounce switch gets a value of 1. So what this means? That means the switch is not pressed. Okay, because when you press it, it will go to the 0 logic, right? So that's is the reset condition. Now what we want? Now we want that when the switch is pressed, then we will increase our counter, right? So write that condition. If sync one signal is 0, means when it is pressed, then increase the counter. So counter is counter plus 1. Okay, so this is happening when switch is pressed. Okay, else now we have one more problem. Like if we leave this statement as it is, then it will start counting and counting and counting and counting again and again at each and every rising edge of clock. But we need to trim our counter to stop counting at some specific threshold. And what is that threshold? We have defined this as a constant. So this is constant debounce period, right? So let's copy it. So we are needing additional condition. What? That only count this or only increase the counter when this condition is met. When your counter is having the less value than your threshold, and your threshold is debounce period. Okay, and then this condition will be met, then we will increase our counter. And if now what it is doing, that it will only count at the rising edge when the button is pressed, switch is pressed, and when counter is less than our threshold value, right? Now we have the second stage of this, that when you release the switch, then your counter start decounting, right? So we will use the same condition. If counter is greater than 0, then counter is counter minus 1, and if. Okay, so what it is doing now, suppose if we don't use this condition, then what will happen? We have this counter value at some specific range, like the maximum range is 2.5 million, right? So when it is at this point, then and when you release the switch, then at every rising edge, your counter start decounting, and there will be state when it will become 0. And if you don't limit this condition, then it will go in the minus values, negative values, right? And we don't want this. So we have stopped it when counter is 0. Okay, so when counter is greater than 0, then reduce the number, and when it is reached to 0, then stop the counter. Okay, and this logic is having one advantage as well. Now we have defined the counter and everything is well till the time. But till now, we have not specified this debounce switch. We have just give the reset condition for this one, right? So we need to specify this debounce switch. Okay. So what it is very simple. So from the last session, when we explained the concept of debouncing, we explained that our debounce switch is treated as a pressed when our counter is reached to the threshold level, right? And what is the threshold level? So let's write the condition first. If our counter reaches to the threshold period, so our threshold is debounce period. So we have defined this constant, remember? Then when it is happened, then that means the switch is pressed. Means our debounce switch signal is pressed, means 0. Else if counter is equals to 0, then we will say that our debounce signal is not pressed or 1. And just terminate this condition, and if and everything is good. Now there is one more step, that we have specified this debounce period switch, but we have not used this for button detection, right? So we need to use this instead of sync 1 signal, right? So what I remember that we have used this sync 1 signal at this place only. Okay. So instead this sync 1, we will use this debounce signal now. Sorry, it's not debounce period, it's debounce switch. So let's copy it here. Let's copy it here. Debounce switch. Everything is good. Okay. So let's do that and just replace it as well. Now we have replaced our sync 1 switch with the debounce switch. Now everything is good. Okay, now let's save it. So I have saved this one. Control S. And now compile our design. So let's compile. Okay, something is not good. Okay, so we have not terminated the process block. Now it is good. Okay, now again. Okay, so this time everything is good. Our design is compiled successfully. Now it's time to program this updated VHDL code with the debouncing system into the FPGA board. Okay, so let's open the programmer once again. Select the hardware. Now select the project and click on Start button. And it's done. Okay, so now let's move to the FPGA board and see if that bouncing problem is solved or not. Okay, so we have gone through the demo and we have pressed the switch few of the times after making the changes, and it looks much better now. Means the logic we have written to solve the bouncing problem of a switch was working well. And I am pretty satisfied with the results now, because our LED pattern is now shifting by one precision when I press my switch on the FPGA board. So that's what we are expecting from our project, right? Okay, so that's it for today. In the future sessions, we will be doing more projects and we will be solving many such problems. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.